All right, I think we're ready to go. If anyone has homework questions, I am free for a few minutes for a quick office hour. Yes.
So for question 1, 2, 3, not like 4.3, 4.3.
Yeah, I get it.
When it says defect, does that just mean you draw like the head-to-head, tail-to-tail, and working out?
Yeah, so when I say head-to-head defect, tail-to-tail defect, those are generally called defects as we talked about last lecture, right? So, you know, since I've been dealing with these concepts for a while, those head-to-head and tail-to-tail are defects in the normal addition of head-to-tail. So I will generally call them defects. You might see that. I honestly don't know if the book calls them defects, but I did mention that in last class, and so you should just be used to that. So there's nothing new about head-to-head defect versus head-to-head addition. You'll just have to adjust to that nomenclature.
Just for the very last question, number 3, for the actual termination scheme, I believe that it's going to be combinational.
Yeah. So hold on, I just got out my homeworks. Draw a reaction scheme for the polymerization of butyl acrylate by benzoyl peroxide. Label initiator conditions, etc. That's all the information you're given, right? So you don't know. You should just draw them both. Yeah. So in order to figure out what is the termination mechanism, you have to be given some information. You have to be given Q. You have to be given the number of moles, because of course the number of moles change depending on the termination mechanism. So you can't know whether it's termination by combination or termination by disproportionation without some kind of information. Just like you can't know Kp or the propagation rate constant unless you have some information on that, right? That's a variable. And so you need to look for clues in terms of what variables you know and what variables you don't know. For instance, someone asked me and you all want to hear this for sure. Someone asked me in 4.4, you know, how do I compute X bar N? Because that's one of the variables that you need to solve that problem. But I promise you that there's enough information in the problem statement as is to calculate the degree of polymerization, because you know what the polymer is and you know what the molecular weight is. And if you know those two things, you know M0, right? And it's really easy to get to X bar N. And so in some cases in the homework, you know, there will be subtle hints. And so, you know, some of the information might not be relevant, right? But things like the density of styrene, you know, that gets you to the concentration of monomer. So you need to think about what information you have and how you take that information and get to the variables that are of interest. And so we're going to talk about that more today, what you know and what you don't know, and how to solve for the variable of interest. But it would be too elementary if I just told you that concentration of initiator is this, X bar N is this, and then plug and chug. You know, this is not a plug and chug class. This is read the problem, understand the concept, find the governing equations or the governing information, and then synthesize that in order to get you closer to the answer. Yes?
For the PLA that we took, could you explain why Q is equal to 0.5?
Yes, that is a very good question. I got a couple of questions on that. So let's just go to Q, because you had to read ahead, right? The PLA is a pre-lecture assignment, so it covers stuff sometimes that we haven't talked about. And this is confusing. So again, you have to remember, where's the definition of Q here? Okay, the definition of Q is what? The rate, go ahead.
The rate of polymers formed by disproportionation.
the rate constant of the disproportionation reaction over what? What is K sub T? The total termination rate. And you know that QT, well, I think that's going to work. You know that QT, geez, sorry about that. KT, sorry, Q's, K's, whatever, equals what? KTC plus KTD. So remember what the definition of Q is, because if you try and make up Q, oh, I think Q is KTD over KTC, you'll get it wrong, right? Because it's not, yeah. And so you have to remember the definition of Q. Now, to answer the question, when you terminate, we just had this slide, when you terminate by combination versus disproportionation, the reactants are the same in both of these reactions, right? So how many chains or how many moles of chains do you have in the reactants of both of these reactions? Not a trick question, right? 2 moles of chains. I have growing chain A and growing chain B, and I have exactly the same 2 moles in disproportionation, same exact reactants. How many moles of products do I have in termination by combination? Yes. Oh, hold on. I want a simple answer. How many moles of products do I have when I terminate by combination? 1. So I go from 2 moles to 1 mole. Now, same question for disproportionation. I start with 2 moles of reactants. And how many moles of products do I have? 2 moles of products, right? Okay, so we're set up. We know that the moles decreases for termination by disproportionation and the moles stay the same for termination by combination. And now we have to apply this to the PLA, right? And so I think the PLA was something like, we have 1 mole of growing chains, right? And we wind up with 0.75 moles of finished polymer at the end. And so it's basically taking these numbers and dividing everything by 2, and then figuring out what fraction is termination by combination and what fraction is termination by disproportionation. So let's just do that. Because I did this problem yesterday by myself. I don't often do the PLAs, but I don't mind doing them to answer the questions. So I start off with 1 mole growing chains. And so my chains are growing and they're going to terminate. And I wind up with 0.75 moles of terminated chains. At the end. So how many moles of this go by combination? And how many moles of this go by disproportionation? So there's various ways you can do this. The easiest way is to do it by inspection. And so we could start with all combination. If I have 1 mole of growing chains and I get all combination, I'm going to have how many moles of terminated chains? 0.5, right? Because I take 1 and 1, or a half mole on the right, a half mole on the left, and I combine them and it's a half mole of dead chains. But the molecular weight is greatly increased, but this is not about molecular weight. If I terminate that 1 mole of growing chains by disproportionation, how many moles of dead chains do I have? 1, right? I started with 1 mole of growing chains, they terminate, and it's the same moles. And so you can take the average of 0.5, which would be combination, and 1, and that gives you 0.75 moles if you have 50% by combination and 50% by disproportionation. So you can reason your way through it, or you can make a little equation and say that I've got 1 mole and I multiply, or these are going to be my combination. Now let's erase that. So 1 mole, and if I do all combination, right, I'm going to multiply that by 0.5 because I'm going to have half the number of moles, plus 1 mole times, and if I do by disproportionation, I'm going to have 1. And so let's call this, and so that's going to equal 0.75, right? And so that gives me the definition of what's happening with disproportionation versus combination. Then I can figure out Q, because Q is not based on these numbers, it's based on how much disproportionation over total. Does that make better sense?
Yeah.
Yeah. It's tricky because the definition of Q is weird, right? It's over the total. And so you do have to intuit the 50-50 part of it. Yes.
Just for that little equation that gets to 0.75, I think it's supposed to divide that.
Oh, sorry. Yeah, sorry. It's my bad. Okay. So that's part of the PLA. Of course, the PLAs are just to make sure that you're reading the lecture, that you're thinking about what we're going to do next, and then we're going to discuss Q in more detail in a second. Any other questions on the homework or anything we've done so far? Okay, I'm going to talk about the radioactivity. I'm going to talk about homework number 4.3 in a second, and we're definitely going to get to 4.4. We have one equation we haven't talked about that you need to answer 4.4, and we're going to talk about that. So that's where we're headed. All right. So remember, we're here. The homework 4.2 should, 4.3 will really get you in the mood for drawing out all these structures, for thinking about what's going on with all these different steps in radical polymerization. 4.2 is a little bit easy in terms of thinking about how the different variables affect the equations that we're going to talk about. And so we're going to get there a little bit further. So the problem with an equation like this, R propagation, right? That's what rate of polymerization, right? Because we're at steady state, is that we don't have a very good expression for the concentration of m dot. You know, I'm not going to give you that in the problem statement. I'm not going to say very often the concentration of growing radicals at steady state is 6 × 10⁻⁷, moles per liter or something like that. But by thinking about how we calculate m dot, we're able to arrive at this key equation right here. And so we've developed an analytical expression for m dot, and all of the things here we know. So we know the initiator concentration initially, that's what we put in the pot, or we can solve for that if we know some other variables. We know F, we know KD, we know KT, because that's the sum of the 2 different rate constants, and we can do that math. So this allows us to basically calculate, or this does allow us to calculate the rate of polymerization based on variables that we know. We can calculate all these things, or the problem statement. If I ask you, what is the rate of polymerization under these conditions? There's probably going to be enough information in the problem statement that you can pick off all of these variables. And so 4.2 is about what happens to the rate of propagation as I change all of these variables. And we practice that. You can get out your clickers, not this one, but we practice that on this type of equation, right? So we're in CD and clickers, and I'm going to have a clicker question in about 10 seconds here. And so we practice that when we, what happens to the total radical concentration if we double the concentration of initiator? And of course, m dot is proportional to the concentration of initiator to the square root, because that's the form, or that's how the mathematics of the equation work, because we have an expression for m dot and the concentration of initiator is under the square root. So that's really important that you're able to see that. And so if I say, I'm going to increase the concentration of initiator by a factor of 10, you know to say that, well, m dot's going to increase by 10 to the 1/2. So make sure you're able to do that type of analysis where you don't necessarily have to plug and chug everything in. You can answer the question based on some of the fundamentals. All right, here is the clicker question. Oh, CD. Okay, everyone's there. All right, what happens to the total rate of polymerization at steady state, because that's what RP is, if we double the concentration of monomer? So if you increase the concentration of monomer, so you need to know what that variable is, you need to go find this equation, because on the exam, I'm not going to say, please use this equation. I'll say the total rate of polymerization at steady state, and you know that that is RP, and you'll have this equation on your equation sheet. What happens if we double the concentration of monomer? All right, perfect, right? 55, 57. Oh, I have to click on here. And so RP doubles. That one's easy because, of course, the concentration of monomer, there's nothing going on with square roots. It's not in the denominator. It's not an inverse relationship. There's nothing weird going on. If you double the concentration of M, RP doubles. And so I don't know why that. Oh, yeah, it's proportional. That doesn't mean anything. Questions? Yes.
So earlier you just said that because what steady state is what RP means. So
Yeah.
when it's in where we make need to use RP, should we automatically assume it's steady state?
Yes, if I don't say it's steady state, I will tell you it's not steady state, or there will be some hints. If I don't say anything, you can probably assume steady state. Yeah. All right. Any other questions? All right, there are some other practice problems. So we have a few things to cover today. So I'll let you check out these practice problems at home, because it is some plug and chug. It's like the homework, but you want to practice these on your own, so we can discuss the things we need to discuss for the homework. All right, moving to note set 12. And here comes my second to last homework hint. And so when you're writing out what's going on in 4.3 part 1, it's a lot of writing, right? You know, there's a lot of carbons, there's a lot of things going on. Don't be shy about using a couple extra pieces of paper, make it big, space it out, because you really want to get used to pushing the electrons, thinking about all the atoms, being precise about what your structures look like. And so this is just the hint that we know what AIBN is. You don't need to memorize what AIBN is, but you need to memorize what it does. And so if we're going to use AIBN for something on the exam, or if I ask you some chemical question about it, you need to know that one molecule of AIBN gives you how many initiated radicals? 2. You have to memorize that. You don't have to memorize the chemical structure of AIBN. Okay. And then the other thing that you really need to know is that as you initiate a polymer chain and as you propagate it, remember this is an N group because that initiated the chain in step 2 of initiation. Remember, that's reaction with the monomer. This is the split of I, and this is the reaction with first monomer. Okay, that's important. But the AIBN fragment is the N group of a growing chain. So growing chains will always look like this. there's some end group that the initiator started, and then there's a radical that's ready to keep propagating, or something else is going to happen to it. And so you want to know what a growing chain looks like, because you want the radical on the right place, right? It's sitting on the head, ready to react with the tail of the next monomer, all of that stuff. And so we can write out a very clear expression for what propagation looks like. And this, of course, is head to tail reaction based on the way we've drawn it. And so we have a new growing chain that adds one monomer. So this looks pretty clear because I did this in ChemDraw. And your book structures are pretty clear. You want to strive to write structures by hand that look a lot like this. I mean, everyone's got their own style. Everyone has their own penmanship, but you want to organize things left to right like a regular chemical reaction. And you want to get your growing chain end to kind of look like this. You want to get your repeat units to kind of look like that. And you want clearly identified end groups. And so what 4.3 part 1 is about is how good is your bookkeeping? How good is your description of what's happening? And it is okay to have this slide up and write it down, try and copy that, because that's how I expect structures to be written. So it's really, really clear what you're doing. All right. Same thing we just talked about, termination by combination and disproportionation. You want to be as clear as possible. Again, there's a lot of things going on, a lot of atoms. You can draw out the phenyl groups if you want. You can do, the hexagon with the circle in it. That's all fine because we're not moving those electrons anywhere. But you want to have really clean nomenclature and clean drawing for your structures. Okay. So the homework discussion. So I give you some information that you've probably never seen before about radioactive AIBN. And all that means is that you're able to count the AIBN molecules. So I don't have to tell you about the moles of AIBN. I can just give you a proxy for how much AIBN is going to be there. And so I say, okay, the AIBN has a radioactivity of 6 × 10 to the 9th counts per second per mole. So counts per second is the radioactivity unit. That's the counts, right? How many counts per second? Like a Geiger counter that clicks, click, 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 click. That's what I'm talking about. And then the other part of the unit is per mole. Counts per second per mole. So if I have 1 mole of AIBN, I know exactly how many counts per second I'm going to have, right? Fine. The hard part about problem number 3 is that I give you the radioactivity of, what are we making? Polystyrene with units of 6 × 10 to the 3rd counts per second per gram. So all of a sudden I have different units, right? I was talking about per moles for AIBN and per gram for polystyrene. And so I have to compare with the same units. What should I do? Should I do everything per gram or per moles? It turns out that the best way to do this problem is to figure out the molar radioactivity of polystyrene. So on a per mole polystyrene basis, what is the radioactivity of polystyrene? You know per gram, right? So it's just a matter of transforming it into per moles. So don't be intimidated by these funny counts per second per mole. Counts per second is the radioactive unit. You move that unit along. And all you need to do is turn grams per gram of polystyrene into per mole of polystyrene. And what information do I give you in order to allow that transformation? Yes.
The number average molar mass.
I give you the number average molar mass, right? I tell you how many grams per mole the polystyrene is, and the polystyrene is just like any other chemical compound. When I know the molecular weight, I can convert between moles and grams. So this is the key to 4 point, where are we? Yeah, 4.3 part 2, sorry, is I have to compare how much radioactivity per mole of AIBN and how much radioactivity per mole of polystyrene. And the key is right here on this slide. For termination by combination, this is the final resulting polymer. How many AIBN N groups do I have if everything is terminated by combination? 2 AIBN N groups. So I've got one here and one here. And remember, these 2 AIBN N groups came from one AIBN molecule, right? The AIBN has a molar radioactivity of the whole molecule, not the N group, not the 1 carbon. And so I have 1 mole of polystyrene and 1 mole of AIBN if they're all terminated by combination. If they're terminated by disproportionation, I only have 1 AIBN group on each chain. And so that means I've got 2 moles of polystyrene that was initially there, and I only have 1 mole of N groups. And so the molar radioactivity of polystyrene is double that in combination versus disproportionation. Remember, it's per mole. Doesn't matter what the molecular weight is. I've already given that to you, but we're talking about numbers of chains with different amounts of N groups. So this problem is a little hard. It's a little bit of bookkeeping, but it's to make you realize that the N groups are different when I terminate by combination versus when I terminate by disproportionation. And that's a really important concept. All right, any questions? Go ahead.
So how do we know exactly which one, like, which combination of this comparison should be used? Just use both again?
Well, so you have to figure out, okay, based on the molar radioactivity of AIBN and the molar radioactivity of polystyrene, how do they compare? Right? Because in one instance, the molar radioactivity of polystyrene in combination is going to be the exact same as the molar radioactivity of AIBN, because it's 2 N groups on each polymer chain, which is basically a polymer chain plus a mole of AIBN because the AIBN splits, right? So in termination by combination, the molar reactivity will be the same for AIBN as polystyrene. For disproportionation, the molar reactivity of polystyrene will be half that, the molar reactivity of AIBN, because there's only 1 AIBN on every chain. All right, that is tricky and it takes some thinking, but remember that when we're talking moles, we're not talking molecular weight, right? We're just talking how many moles compared to how many moles. All right, that's my second to last homework hint. I will give you the last one in a couple minutes. We'll make it. All right. Any questions or comments before we move on? All right, so this is a key equation right here. It was in a green box on previous slides because we know all the variables. We can identify it very well. We can also calculate things like rate of initiation because we know all of those variables, right? Unless we're given the derivative, it's hard to calculate RP from this equation because you don't know what that is unless there's some information. We don't have a great equation for M dot unless we substitute things in. And so make sure that you familiarize yourself with the equations that we can generally solve from the variables that we're going to discuss in the problems versus the equations that are just intermediate to the derivation. That's a little bit tricky. All right, you can do that problem on your own because that's a lot of plug and chug. Okay. So rate of propagation is great. That's fine. We talked about that. We have an equation for that. But if we're talking about polymers, we really want to know X bar N, right? So you all remember what the definition of X bar N is. And before it was moles of monomer transformed into polymer versus total moles. This time we're going to add T, which is the moles of monomer consumed in time T, over the moles of polymer formed in time T. We just have to add that rate in there because we're talking about a rate. Questions? Go ahead.
So would we have to consider like how this multiply again, multiply by two, and if there's like two reactions, two different monomers, to look at different condensation reactions?
This is only for addition. So we're only talking addition here because this is under free radical polymerization. So we're not talking about any condensation polymers right now. Yeah. So this is how we want to calculate X bar N. And the question is, how do we get at these variables based on what we know? So the moles of polymer formed in time T. Remember, it goes back to the termination, right? Because we get different moles of final polymer depending on what the termination mechanism is. So the rate of polymer formation is going to be our termination expression based on if we're terminating by disproportionation versus terminating by combination. If we know those rate constants, they've got the same reactants, right? So we can develop what that rate is from this. And then we have, well, we already know the other variables. And so we know the moles of monomer consumed in time T, because that's rate of polymerization, right? That tells us how many monomers are transformed into polymer. Now we know how many moles of polymer are formed from the termination. Remember, this is RP. And so we can get X bar N, and we put a 0 there for a very good reason, because there's no chain transfer. So 0, X bar N sub 0 for free radical polymerization means no chain transfer. And so if we simplify this out, here's our degree of polymerization with no chain transfer. And then we look over here and we say, do we know all these variables? So where do we find Kp? Has to be given somewhere in the problem statement, right? How do we calculate the concentration of monomer? It's going to be given in the problem. Density. Remember, if you know the density, you know how many moles per centimeter cubed there are, how many moles per liter there are. Remember, concentrations are in moles per liter. Always don't make up a concentration unit. Take the unit you have and turn it into moles per liter, and you can't be wrong.
That's why we do it in bulk, correct?
So that is a very good point. So we don't know what bulk polymerization is, but in that problem, you might be able to intuit that there's no solvent. So there's no solvent diluting the concentration. So you can take the density of styrene and change it into a monomer concentration. Yeah. We can figure out what Q is based on the definition of Q. And we need to know something about the efficiency of the initiator and the decomposition rate constant of the initiator, and we need to figure out the initiator concentration. But these are all things that we can figure out if we have enough information in the problem. Or as the homework says for, let's see, I think this is 4.4, is that it asks you about the initiator concentration. So it gives you a bunch of information. You have to make a little table, what you know, what you don't know. And it says, please calculate the initiator concentration for this situation. So remember, we only have one equation. And so we're probably going to have to figure out what's the one thing that we don't know. So we don't know the initiator concentration in that homework problem. And so the only thing that we're really not given explicitly is X bar N 0. And so the piece of information that you need to track down for 4.4 is how do you get X bar N 0 from the information given? So how do you figure that out? Has anyone done that? Yes.
Just MN over M0.
That's right. It's Mn over M0. And I tell you what the polymer is, right? As soon as I say polystyrene, or as soon as I say polyethylene, or as soon as I say polyvinyl chloride, you're like, boom, I've got M0. I either need to know the degree of polymerization or the molecular weight, and I can get the missing variable. So the key is that you need to solve this equation for the concentration of I, because you know everything else. And so it should be easy, right? It's just an algebra problem, but take it step by step, because I'm not going to give you an equation that says concentration of initiator equals, and you can just look at that and write it down. You have to rearrange this thing. And remember, the key part of this, as I was talking to someone on office hours yesterday, is this is all multiplied together. There's no pluses, there's no minuses in there. They were, the person I was talking to was insisting that they couldn't solve for I because they couldn't factor it out. There's nothing to factor here. You just have to rearrange everything. Don't forget that I is under a square root as well. And so that's going to change things as well. That might, you know, if you get factoring and you're good at algebra, that might be obvious, but this was the #1 question aside from the radioactive question. This was the #1 question in office hours yesterday, is how do I solve for concentration of initiator given this equation? Should be easy, right? But there's lots of stuff going on. So careful bookkeeping, take it step by step. Any questions? Yes. So yeah, you have enough information to calculate Q. Just calculate that, and then what's the oh, and you can calculate the concentration of monomer, right? We might call that square brackets M, just to make sure that. That's right. And I mean, you need to take the density of the monomer and turn that into moles per liter. Yeah. Yeah. So, I mean, it's a long problem. I mean, it's just like 4.3 part 1, you know, take it step by step and you can figure it out. But again, I wanted to give you a hint on this and have a discussion about it, because it's not always going to be plug and chug. I'm not just going to ask you, what's the degree of polymerization given all this stuff? Sometimes you're going to have to go and find the variable that I'm talking about. I know everyone's tried this, tried to figure it out before they came to lecture today, so you know exactly what I'm talking about. And if you don't, I will try and answer questions by email or after class today. But, you know, if you email me at 7 p.m. tonight, you know, no promises. Any other questions or any other comments before we start moving on here? Okay. You guys know how to handle all these equations. Now, the key is that this is X bar and 0. So no chain transfer. And we already talked about the definition of Q. That's great. All right. And so we've got these relationships. So you can get out your clickers. So the expression we derived for X bar and 0 was without chain transfer. Now imagine that we add chain transfer to the polymer. So we move the growing end from one polymer to the other polymer. How will Xn with chain transfer compare to Xn sub 0? And you can get this from the definition of X bar N. So you have moles of monomer consumed in time t versus moles of polymer formed in time t. And what's the key about chain transfer to polymer? You just move the growing chain end or the growing radical center from what to what? One polymer chain to another polymer chain, right? So the monomer's just sitting there. Polymers are changing who is the growing chain end, but has any situation changed with the moles of monomer or the moles of polymer? No, that's right. Perfect. No, no change. They're the same. So you can ring in. Oh, we're at 57. We've lost a couple people. So no change. They would be the same. And that's why I told you 2 lectures ago that when we have chain transfer to the polymer, there's no change in molecular weight. So that's what's complicated about chain transfer to polymer is just drawing those structures and figuring out if it's a short chain branch or a long chain branch, but there's no change in your degree of polymerization. You go from polymer to polymer, we don't know any different. All right, next clicker question. The expression we derived for xn0 was without chain transfer. Now, what's going to happen if we add chain transfer to monomer? So chain transfer to monomer means that you take a growing chain end from a polymer, that radical that was sitting at the end of the polymer, right? Then you move it to the monomer. And so in that process, the polymer terminates and you start a new chain based on that monomer. And so what happens to our definition? Moles of monomer consumed versus moles of polymer formed. So all of a sudden we've made a polymer, right? When we transfer that growing chain end off of the polymer, we've made a polymer and we've consumed another monomer. And so x bar n0 is greater than x bar n. And we can, well, let me stop the clicker here. And we can think about this. The degree of polymerization will decrease because we have more polymer chains formed. And so the denominator increases. We actually chew up the numerator a little bit too, but, and so x bar n goes down. But the main thing is that we form a polymer and terminate it without consuming any monomer. So the denominator goes up. And so this is always going to be the case that with chain transfer to anything but the polymer, x bar n0 is always going to be greater than x bar n. And this is the special case. So the special case is when you have chain transfer to polymer, no change in degree of polymerization, x bar n equals x bar n0 equals x bar n. That's the special case, chain transfer to polymer. You can think about it. If I have a growing polymer and I move it to another growing polymer, nothing changes except for the branching. Versus in all cases where I chain transfer to the chain transfer agent, chain transfer to the solvent, chain transfer to the monomer, I'm always going to decrease the molecular weight of with chain transfer compared to without chain transfer. And the polymer, excuse me, the polymer industry uses this to limit the molecular weight of polymers that we buy. So the polymer industry doesn't say, we're going to make the awesomest, longest polymer molecules ever. We want super high molecular weight. And that's going to work for everything. It turns out that the polymer industry makes different molecular weights for different things. And they use chain transfer agents to control that exactly. And they change monomer concentration. They change initiator concentration, all that stuff. And you'll learn a lot about chain transfer agents in your advanced classes. But this is a key concept that chain transfer agents generally decrease the molecular weight. Questions, comments? All right. Okay, that's great. So the question is, how do we get a handle on the kinetics, right? We were talking about the kinetics, rate of polymerization, rate of termination. It turns out that we have a kinetic expression for the rate of chain transfer. And this is where it gets a little bit complicated, but we have a simple equation for this that I'll show you in a second. So this is with no chain transfer, because this is x bar n0. And what do we do with this m dot? So I just wrote this equation, but how do we handle concentration of m dot? We have an expression for that, right? And we can simplify. So you'll see this equation on your equation sheet for the exam, but you'll also see, you'll also see this equation, x bar n 0 equals all this other stuff that we know, because we have just substituted in our expression for m dot and simplified. I'm not going to draw it out on the board for you. You can go home and do that tonight if you want to, because I know you're going to have some extra time on a Friday night. But sometimes you'll get to a point doing the homework, doing the exam or a PLA where you're like, I don't know what m dot is. Don't forget, you can calculate m dot based on some of the other variables that we've talked about. All right. Where were we? We're right here. So chain transfer is going to limit the molecular weight, and chain transfer to monomer, initiator, or solvent, right, makes a dead chain. It's not called termination because we're not disposing of the radical, but we're stopping a growing polymer chain. So it looks like we're terminating the end of a growing chain. And so this was our expression for termination by combination and termination by disproportionation. That was in there already. That's right here. And so we just add other ways growing chain. And this can get really unruly because we have a bunch of rate constants now. So we have KTR, which is K transfer to monomer, K transfer to initiator, and K chain transfer to solvent. And we can write equations for all that if we want to. So we could put our different K, are they capital T? Nope, small t. KTR right here. And since we just specified that TA is a chain transfer agent, we'll use, no, we don't have a KTA, but this is the rate constant for the chain transfer reaction. So this can be monomer, solvent, initiator. So this is a handful, and so we have a simplified expression to handle that, and the way we do that is just with a little math and rearrangement. So this is our new expression for x bar n with chain transfer, because there's no zero there. And it turns out that two polymer scientists, one named with the last name Mayo and one with the last name Walling, came up with this Mayo-Walling equation. And so this is going to be really useful because we can figure out now what the x bar n is given what the x bar n0 would have been. That's without chain transfer. So we can figure that out. We have an equation for that. And then we have these things, which are just called chain transfer constants. And so there are lots of tables of chain transfer constants. There aren't lots of tables of KTRM, KTRI, et cetera, but we can look up these chain transfer constants. Yes.
So I know that for the XN where you had M minute for X0 also, is that equal also be just with chain transfer, or is that just X0?
Yeah, so you have to know based on the problem. If I give you information about like the molecular weight and the M0 and you're trying to calculate x bar n, if I say without chain transfer, the molecular weight would have been this, then you know that that's x bar n0. If I don't say anything from the problem, I might say something like the molecular weight of the chains are 5,000 grams per mole for polystyrene, and there was chain transfer involved in that, which means you're probably solving for x bar n, right? So I'll be clear whether chain transfer was happening to get that molecular weight or chain transfer wasn't. But in this equation, because we have an expression for x bar n0, you can generally calculate x bar n0 given the information in the problem, because you need to know most of this before you start to apply the chain transfer constants. Does that make sense? Yeah. So that's a key point, that both of these are hard to calculate, right? X bar n from the Mayo-Walling equation, and I'll give you an example here in a second, but X bar n0 is also difficult to calculate because you either need to know something about what the molecular weight would have been without chain transfer, or you need to have all of this information to be able to calculate X bar n0 on your own. And generally it will be like this. You have to go find all those variables, calculate X bar n0, and then apply the chain transfer constants to get X bar n. So that's a two-step big problem. Any other questions? All right, we still have a few minutes. We're going to make it all the way through chain transfer constants. So this is really cool. This gives you the chain transfer constant, KTRTA over KP. So you can use that in the Mayo-Walling equation. And then it tells you exactly what bond is cleaved for these different compounds. And there are lots of tables of chain transfer constants out there. So we are building up our quantitative part. I noticed on exam 1 that lots of people liked the equation part of exam 1, did well on that. There were some weaker chemistry parts on exam 1. In exam 2, now you'll be ready for, okay, this is the chemistry. I have to figure out how to push these arrows. I have to figure out what free radical polymerization is. But there's even more quantitative mathematics on this. It's all algebra. It's all relatively straightforward, but you need to keep your wits about you in terms of solving these equations. Questions? All right. Last thing that I want to cover today is this idea of an inhibitor or retarder. So inhibit means stop or prevent, which means there's nothing happening. And a retarder means slow down. And this is interesting because this looks different depending on what's going on. And these molecules come from different places. So if I'm going to ship a train car of monomer, and it turns out if you look, the train tracks outside of Philly, there's some big black tanks, and they say styrene on the side of them. Styrene is a monomer. It's going to become polystyrene. Do I want to inhibit making polystyrene in that tank, or do I just want to slow it down as that rail car's going to Wilmington or something like that? I want to inhibit it, right? I want to have zero polymerization. And I'm going to use something like DPPH or BHT. There's all sorts of different inhibitors, but this stops polymerization. I don't want to retard polymerization because that means the polymerization is still going to be happening. However, we run a lot of polymerizations under oxygen-free conditions because, well, because I don't know why. Because it slows down the polymerization. Let me see if I can get this going. I want to show you one more slide. And so what this looks like, if I can get this one slide back, hold on one second. So slide 25, here we go. Slide 25 gives us now this kinetic curve, time versus conversion. How are we building up molecular weight? An inhibitor stops polymerization for a certain amount of time until the inhibitor is also used up, and then it goes. And a retarder just slows down polymerization versus what it would be. So now you have all the information you need for the homework. Ask questions. Turn in your homework tonight. Don't forget the PLA this weekend, and I'll see you on Monday. Thank you very much.